Hello guys, welcome to my YouTube channel Physics Brings. My name is Deepak. I'm going to teach you all 9 subjects of physical science in detail. My courses are absolutely free of charges. My courses are going to help the students who are preparing for CSIR, NET, GATE, NT exam, PhD exam, SET exam, Jest, Tifr, IIT-Jam and other exams related to physical science. Okay, so this is the lecture number 24 of mathematical physics, in which we are going to study singularity, okay, of complex. So I'm going to start now. Before starting the class, I would request the students who haven't subscribed my channel yet, please subscribe my channel and watch my free live lectures, which are going to help you to crack the exams related to physical science. Okay, so we are studying complex analysis. In complex analysis, we are studying singularity. Okay, so I'll start now. I'll check the sound, whether I'm audible or not. Let me just check. Free live lectures, which are, yes, I'm audible, so I'm going to proceed now. Okay, so singularity of a complex function. Okay, singularity of a complex function. Singularity of a complex function. Okay, so singularity of a complex function we're going to study. Okay, so I'll give example first. Okay, so suppose there's a function fz. Okay, fz equal to 1 upon z minus 1. Okay, so this is a function, guys. 1 upon z minus 1. Okay, so we'll put denominator equal to 0, z minus 1 equal to 0. That implies the value of z equal to 1. So if you put z equal to 1 in this expression, right, so this fz is going to be infinity, right? So this means uh, z equal to 1 is singular point. Okay, singular point. If you put the point in the expression, and then that expression becomes infinity, means that that value is a singular point. Okay, so in this case z equal to 1 is a singular point. Okay, second example is fz equal to 1 upon z minus 1. Okay, and z minus 2. Okay, so here z minus 1 and z minus 2 equal to 0, and this implies value of z equal to 1 and 2. Okay, so if we put z equal to 1 and z equal to 2 in fz, this value is going to be infinity, right? So it means z equal to 1 and z equal to 2 is singular point. Okay, singular point. Very simple, right? Next is isolated singularity. Okay, isolated singularity. Isolated singularity. What is isolated singularity? Okay, isolated singularity. So a point z equal to z naught is an isolated singularity, is an isolated singularity singularity if fz is if fz is not analytic fz is not analytic at z equal to z naught. Okay, fz is not analytic at z equal to z naught. Second is fz is analytic in the neighborhood of analytic in the neighborhood of z naught. Okay, so fz is not analytic at z equal to z naught, but fz is analytic in the neighborhood of z naught. Okay, for example, then this is isolated singularity, then z naught is a isolated singular point. Okay, so for example, fz is going to be, if in this case if fz is a function of z minus 1 and z minus 2. Okay, so here this is the case, this is z minus 1, this is z minus 2. Okay, so this is at this point function is not analytic, but at around this point, right? So in the neighborhood of this point and in the neighborhood of this point, function is analytic. Okay, then z, it means z equal to 1 and z equal to 2 are isolated singular point. Okay, so at z equal to z naught is not analytic, but z at, okay, the point z naught is not analytic at z equal to z naught, but it is analytic, but function is analytic in the neighborhood of z naught. Okay, then these points are called isolated singular point. Okay, next is non-isolated singularity. Non-isolated singularity. Non-isolated singularity. Okay, non-isolated singularity. So this is fz is not analytic. Fz is not analytic at z equal to z naught. Okay, so fz is not analytic at z equal to z naught. Okay, and second is there are singular points in the neighborhood of z naught. Okay, so fz is not analytic at z equal to z naught, and there are similar points in the neighborhood of z naught. Okay, so this is the condition for non-isolated singularity. Okay, I'll give the example. So if, for example, we have this fz equal to 1 upon sine z. Okay, so for singular point sine z, denominator equal to 0, that implies sine z equal to sine n pi. So n pi sine n pi, so that means z equal to n pi. Okay, z equal to n pi, so where n equal to 0, 1, 2, 3. Okay, so this means there will be cluster of similarities, cluster of similarities as n tends to infinity, right? The value of this value of n are infinite, right? So there will be cluster of singularities in n tends to infinite, right? So this is non-isolated singularity case. Okay, so non-isolated singularity, non-isolated singularity case. Okay, so this is about, so this function is example of non-isolated singularity. Okay, so there are infinite value of singularities. Okay, so this is non-isolated singularities. Now I will categorize that. I will classify these singularities: singularity, singularities. Okay, so these are two types of singularities. One is isolated and one is non-isolated. Okay, so isolated singularity, and this is non-isolated singularity. Okay, isolated singularity and non-isolated singularity. Okay, and non-isolated isolated singularity is divided into three parts. So number one is removable singularity, removable singularity. Number two, non-essential singularity, uh, non-essential singularity, and number third, that is essential singularity. Okay, so these are, so isolated singularities is of three types: removable singularity, non-essential singularity, and essential singularity. Okay, non-essential singularity is also called pole. Okay, this is the classification of singularities. Okay, next point. So next point is so we'll discuss removable singularity. Okay, removable singularity. Okay, so this is principal part means non-negative negative powers of that. Okay, principal part is not present in Lorentz series expansion. So principal part is not present in Lorentz series expansion. Okay, that is no negative power of Z. Okay, so removable singularity means there wouldn't be any negative power of Z. Okay, so I will solve one question, then it will clear your doubt. Question is, as example, fz equal to sin z upon z. Okay, so we'll solve it. So there are three methods which I'm going to use. So I will solve it. So this is the one, right? And I will solve it by first method. First method is I can write fz equal to 1 upon z, and I can open sin z. Okay, sin z means z minus z cube upon 3 factorial plus so on. Okay, so fz is going to be z, I will take z inside, so this is going to be 1 minus z square upon 3 factorial plus so on, right? Because z will cancel, this is 1 and z square, right? So here you can see there is no negative term, right? No negative term of z, and here here we have to find z equal to 0. So if you put z equal to 0, it will give infinite value, right? So z equal to 0, so we can write fz equal to 1 minus z minus 0 whole square by 3 factorial plus so on, right? So it means z equal to 0, okay, is is removable singular removable singular point, okay, is removable singular point. Okay, so z equal to 0 is removable singularity, or we can say removable singularity. Removable singularity. Okay, removable singularity. Okay. So now, so for this function, z equal to 0 is removable singularity. Okay. Next method, second method. Second method is what we are going to do. Limit z tends to 0, that is z tends to z naught, general case, z tends to z naught, z tends to z naught, fz, okay, z tends to z naught fz. If this exists, limit this exists, okay, exists, it means z equal to z naught is singular point, removable singularity, okay. Okay. So it means we'll write this limit z tends to z naught, and value of fz is sin z upon z, okay, and we know, and that is value is 1, because limit sin z upon z value is, this value is 1 always, okay, you need to note down. So this is 1 means exists, right? So it means z equal to 0 is removable singularity. Next, third method is very important. Most of the time we use third method, okay. So third method is limit z tends to z naught, z minus z naught fz. If this value is 0, it means z equal to z naught is removable singularity. Removable singularity. Okay, so we'll check it. Check by this method. So this is going to be limit z tends to z naught for this function. Okay, z minus 0 into sin z upon z. Z will get cancelled. Sin z and z tends to 0 is going to be 0. So this implies z equal to 0 is removable singularity. Removable singularity. Okay. Next question. Next question is fz equal to e to the power z minus 1 upon z. Okay, this is a function, and we need to check whether z equal to 0 is removable singularity or not. Okay, so z equal to 0 is a singular point, right? So we need to check it's a removable singularity or not. How? So we'll use uh, three method all. Okay, so first method is fz equal to, So this one, e to the power z minus 1. So I will open e to the power z. Okay, so 1 upon z as a common, e to the power z I'm going to open. So this is 1 plus z square upon factorial 2 plus 1 minus 1, right? I have just opened it, e to the power, expand the e to the power z and everything else, right? So I will take z inside, so it is going to be 1 upon z. Okay, so z is here, and 1 will get cancelled, guys, here, right? So this is going to be, so we'll take z inside, so this is going to be 1 plus z upon 2 factorial plus 1. So we can see there is no negative term of negative power of z. It means z equal to 0 is removable singularity. Okay, second method is limit z test to, I have already explained second method, z test to 0 and e to the power z minus 1 upon z, right? So this should exist, right? So now what we'll do is we'll check it. Okay, so this is going to be, so here if you put z equal to 0, so this is going to give 0 by 0 form, right? So we'll use L hospital rule, right? So what we are going to do, psi dash z upon phi z dash, right? We are using L hospital rule at L hospital rule. Okay, L hospital rule. So this is going to be, so if we differentiate it, so it is going to be e to the power z will remain as it is, e to the power z upon 1, because we have differentiated. Now we will put z equal to 0, so 1 upon 1, that is 1. So it means finite value, this is exists. That means z equal to 0 is removable singularity. Removable singularity. Removable singularity. Okay. Well, third method. So I'm explaining how to check removable singularity. Okay, third method is simple, important, like limit z tends to infinity z minus 0 into fz is e to the power z minus 1 upon z. Okay, so this is going to be, now z will get cancelled, so limit z tends to 0 e to the power z minus 1, right? Now we'll put z equal to 0, so this is going to give value 0. Okay, 0 means, because if we know, right, third method, if this value is 0, it means z equal to 0 is removable singularity. Okay, next question is, fz equal to sine cube z upon z cube, right? And we need to check whether it's a removable singularity or not. Okay, so whether z equal to 0 is removable singularity or not. Okay, so what we'll do, so we know three method, right? So I'm going to use third method now for this third method. So you can use any one of the method. So third method is limit z tends to 0 z minus 0 into sine cube z upon z cube, right? Z will get cancelled, So this is going to be limit z tends to 0, and this is going to be sine upon z whole square into 1 upon z. Okay, so this value is, we know, right? Limit sine z whole square, this value is, since we know limit z tends to infinity sine z upon z whole square, value is 1, this is z. Okay, so this is going to be limit z tends to infinity in, this is 1, right? 1 upon z. Now if you put z equal to 0, so this value is going to be infinity. Okay? It's not finite value, this value is infinite, right? But this should be 0, right? But it's a infinite. It means z equal to 0 is not removable singularity, is not removable singularity. Okay, next question is, so I have used this method. Okay, okay, no, we have done some mistake, I think. This is something mistake we have done. So this is not z, guys, this is sine z, that's why we mistake. Okay? So sine z is here. Okay, sine z, so this value is 1, so limit z tends to infinity sine z. So if you put z equal to 0, so it is going to give 0 value. It means z equal to 0 is removable singularity. Removable singularity. Okay, this is removable singularity, guys. Okay, so we have made mistakes. So okay, so we have corrected now. Okay, so it's a removable singularity. Okay, okay, so other method you can use it. Okay, and solve it. Now next is non-essential singularity. Okay, second type, non-essential non-essential singularity. Non-essential singularity, or we can say it pole. Okay, very important, guys. There is a question which is asked. Okay, I'll solve that question as well, which is asked in NET. Non-essential singularity, that is pole, also pole. Okay, so this non-essential singularity means finite terms in principal part of principal part of Lorentz series expansion. Lorentz series expansion. Okay, so finite terms. Okay, so principal part. Okay, so there would be finite terms in principal part of Lorentz series expansion. So terms will be finite. Okay, okay, and limit fz at z tends to z naught. Okay, if you put limit fz at z tends to z naught, that value will be infinite. Okay, this value, if you put limit fz at z tends to z naught, then this value will be infinite. Okay, so now I will solve it. I will I'm going to explain it by example. Okay, for example, and also you need to know there so order of pole. Okay, so z, if z equal to z naught is giving infinite, and if you have to find order of pole. Okay, so this is essential singularity, right? Pole. So we have a point z equal to z naught, and that point is giving limit fz to fz, limit z tends to z naught fz equal to infinite. Okay, so in that case we need to because it's a essential singularity case, right? So we have to find the pole of that point. Okay, so how to get it? Okay, so pole of pole order of the pole. Okay, so we have to find order of the pole, order of the pole. Okay, order of z equal to z naught is order of the pole, and this is the case of essential singularity. Now we need to find out the order of pole. Okay, so how to find it? So what we'll do is there's a condition, that is limit z test to z naught will put, and then z minus z naught to the power n fz, and that should exist. Okay, that should give finite value. And the main point is this one: first non-zero first non-zero value of n for which limit exists. Okay, limit exists. Okay, very important point. First non-zero value of n will take for which limit exists. Okay, so I will explain it by example. So example is, this is fz equal to given 1 upon z minus 1 to the power cube, right? Very important question. Whole cube. Okay, so this implies, so we need to find order of the pole. Okay, so this implies z minus 1 equal to 0 and implies z equal to 1. Now we need to find out order of the pole. We'll use this method, limit z tends to z naught, that is z tends to, because z equal to 1, right? Z tends to z1, and that is z minus 1. Okay, and 1 upon z minus 1 cube, right? So first we'll take z minus power 1. Okay, so in that case we are not getting the value, right? Again we'll do limit z tends to 1, z minus 1 to the power 2. We'll take n equal to 1, 2, 3. Okay, respectively. So this 3. Again z minus 1 will remain, so it will give infinite value, so it is not existing. Again what we'll do is we'll limit z tends to 1, and z minus 1 to the power 3 will take into 1 upon z minus 1 to the power 3. In this case, right, this will get cancelled and value is 1. So implies exists, right? For this for n equal to 3, the limit exists, right? Implies order of the pole n equal to 3. Okay, right, order of pole is 3. Okay, for z equal to 1, order of pole is 3. Okay, n equal to 3 means order of pole is 3. So order of pole is 3. This is in this way we will find out the order of the pole. Okay, so now there is a question which is asked in CSIR net June to, September 2022 question, recent question, guys. Okay, so question is, this is, just give me 1 second, guys. Okay, this one is done. Yes, so this question is asked, this question is CSIR net September 22 question, guys. Okay, September 22 question. So question is fz is given, guys. Okay, fz is given. Fz value is 1 minus z minus sin z. Okay, so this is the fz value. Okay, fz is this, and z equal to 0 is a pole of order that order you need to find out, guys. Okay, and options are given. Option A is 1, option B is 2, option C is 3, and option D is 4. Okay, so this is the function given, and z equal to 0 is a pole of order. So z equal to 0 is a pole, and then we need to find out order of the pole. Okay, so how we are going to solve it? Simple way. So we know the method, that is limit z tends to 0 and 1 upon z minus sin z. Okay, if we put this, we can see this value is infinite. Okay, we can see this value is infinite, means this is a case of non-essential singularity. Okay, case of non-essential singularity. Now we've got it that this is the case of non-essential singularity because this value is infinite at z equal to z naught. So what we'll do is now we'll find out the order of the pole. So how to find out? Limit z tends to infinity, and here we'll take z minus 0 1 upon z minus sin z. Okay, so in this case you can see that, right, if you see it, this is not going to give the finite value, right? So what we'll do is now we'll do z equal to just give me 1 second, guys. Okay, okay, so so this is sin z. Okay, this one. So in that case this is not going to give the value. So what we'll do is this is not going to give. Now we'll z to the power 1 not giving the value, then we'll put z to the power 2. It is also not giving value, guys. So at last we'll put z to the power 3. So in that case this is going to be limit z tends to 0. Okay, z cube upon z minus z sin z. Okay, z sin z. Now you can see this is a form of 0 by 0, right? Because sin z value is 0, z value is 0. Okay, so we can use L'Hospital rule. Okay, so in that case what will differentiate it. Okay, and we are going to differentiate it with so we'll differentiate 3 times. Okay, so so if we differentiate 3 times, this is going to be z tends to infinity. The first time it is not work, right? So if you differentiate first time, so this is going to be 3 z square upon 1 minus sin z is cos z. Okay, so in that case again this is not giving finite value. Okay, again we'll differentiate it. Okay, so this is going to be limit z tends to 0, and this is going to be 6z upon this differentiation going to be minus cos z means minus sin theta means plus sin theta plus sin x plus sin z. Okay, so again it will not give the value, so again we will differentiate it 3 times. Okay, power we are going to take, understand this, guys, very important. So first power is not going to work, second is not going to work, then we have taken power 3. Okay, and then first differentiation we have done, that is not giving value, then second differentiation, then third times we will do differentiation. So this is going to be 6, differential of 6, that is 6 upon sin z is cos z. Now if you put z equal to 0, it is going to give value 0, cos 0 is 1, right? 1, that is 6, that is finite value exists, right? So it means n equal to 3, that is n equal to 3 is the order of pole, right? So it means order of pole is that is z is 3. So which option is matching, guys? Very good question. C. Okay. Next, essential singularity, guys. Okay, essential singularity. Essential singularity. Essential singularity. Essential singularity. Okay. So in essential singularity, principal part means the negative powers of z. Okay, principal part, the negative powers of z will be infinite number of terms. Okay, so the negative power of z terms will be infinite. Okay, so principal part means that is infinite number of terms. Okay, and so there would be infinite number of negative power of z. Okay, that's what this sentence is saying. Okay, and now limit z dash to z naught, z minus z naught to the power n fz. Okay, that shouldn't be equal to 0. Okay, so here what we are, so in non-essential case we have seen the principal part is there are finite number of negative power of z, right? But in this case there would be infinite number of negative powers of z. Okay, and again we'll check it. So if limit exists, then that would be the order, right? So for example, I'm going to give example, it will clear your doubt. Okay, so this is e to the power 1 upon z. If you talk about e to the power, so this is the so I'm giving you example of non-essential singularity. Okay, so if we take function e to the power 1 minus z, okay, so that is the example of essential singularity. Okay, how? So 1 upon z will expand it. Okay, so in that case, if I'm going to expand it, so this means 1 plus 1 upon z, one plus z. Okay, so if you put this value, right, z equal to z, so this is not going to be value 0. So 1 upon z equal, if you expand this, this is going to be 1 plus 1 upon z upon 1 upon 2 factorial z square plus so on. Okay, so here you can see clearly that there are infinite number of negative power of z. So this is the example of essential singularity. Second example is e to the power 1 upon z minus 1. So this is going to be 1 plus 1 upon z minus 1 plus 1 upon 2 factorial z minus 1 whole square plus so on, right? So here you can see there are infinite number of negative power of z. So z equal to 1 is essential singularity. Okay, is an essential singularity. Okay, essential singularity. Well, guys, this is about the singularity. Okay, and before ending the class, I would request the students who haven't subscribed my channel yet, please subscribe my channel and watch my free live lectures, which are going to help the students who are preparing for CSIR, NET, GET, NT exam, PhD exam, and other exams related to physical science. Okay, and they can easily crack those national exams. Okay, so okay, guys, bye now. Bye now. Good night.